All right, thank you. So Natalie Johnson is one of our um, top analysts in the Northeast region, and she's going to be providing us with a technical presentation. She's going to be uploading her presentation, given that it's got a few animations embedded into the actual presentation. But this one is a really interesting one, and Natalie actually presented this very topic at the AHS East Coast Conference this past October. So I am delighted to introduce Miss Natalie Johnson, who has actually a PhD, and we rely on her a lot when it comes to all things PFAS, in addition to some innovative approaches that the Northeast region is implementing into their projects. With that, I'd like to introduce Natalie Johnson.
Thank you, Millie. And I really am grateful for the opportunity to speak to all of you today. Before I get into it, I would like to say very much welcome any feedback on this particular project that we've been working on. If we missed anything, if you think there are other questions we could potentially answer with our existing data set, that would be wonderful. And then more broadly, if you think that there are topics, sort of research topics where DEP could potentially contribute to benefit the practice of waste site cleanup, we would really love to hear those ideas. We think that our strengths are in access, both access to data and information, and then also to physical sites. And so we like to think of ways that we could potentially use those strengths to make things better for everybody else. So now getting into this presentation here, the big picture question that we're really trying to address here is not a new question. The idea is, will my remedial technology potentially make things worse? So could we exacerbate an existing issue or potentially create a new issue? And we think that practitioners are generally thinking of these questions. So it's not, like I said, it's not a new question. But what is new is this world of PFAS. We expect that PFAS will be a co-contaminant at some, potentially many, industrial waste sites. And as a co-contaminant, we need to think about how our remedial technologies, which may be targeted at other contaminants, could potentially impact the PFAS. And so that's where this presentation comes in. So specifically, we're motivated by our work at the General Chemical Corporation site, which is located in Framingham in the Northeast region. This site is it's been around a while. It's been in the system for a while. It was used as for oil storage. It was also used for solvent reclamation. And there are a lot of different types of contaminants on the site. And it's also a bit unique because MassDEP was given a good chunk of money to actually perform investigation and remediation at this site. And so we are more involved in this than we would be in a typical remediation. Our charge is essentially to remove as much contamination as we can with the money that we have. And so we are targeting DNAPL, which is extensive at the site. The image here is an image of the site. It's not very large, but there's DNAPL existing across, or thought to exist across, a pretty large extent of the site. And then, as I mentioned, PFAS, it's a co-contaminant here. There was a fire suppression system. There was a tank that was stored inside the warehouse, which is outlined in red there. That tank contained aqueous film forming foam, or AFFF. We also know of a fire suppression system outlet, and then there was a stormwater system. So all those areas are circled in red. Those are thought to be the PFAS source areas. PFAS data from the site does indicate impacts from AFFF. And so our primary goal here is to deal with the DNAPL, the chlorinated VOC DNAPL, which is PCE, TCE, and also 111 TCA. And the plan was to in situ thermal remediation, which, for those of you who aren't familiar with it, the idea is that you basically heat up the groundwater in the soil to the point where water is boiling, and then you apply a vacuum to the vadose zone to remove the vapors. And you can remove a lot of contaminant mass in a short period of time. But our concern is that using this technology could potentially exacerbate the PFAS contamination by taking currently immobile PFAS, making them more mobile, where they could then migrate down gradient. And there are some private wells down gradient of the site. So what is AFFF? Understanding the nature of your PFAS is pretty important if you're going to think about how your remedial technology may impact PFAS on the property. So there's essentially three categories of AFFF. The original one, which I will just gloss over because it's not really relevant to this presentation, but the first one was produced by 3M. It contained mostly PFOS and other precursors to PFSAs. So talking about like PFHXS and PFOS are generally the two compounds that you see. Then the next generation of foam, we call them legacy fluorotelmer foams. And those are a completely different structure. They're made up of polyfluorinated compounds, which you can see some here on the left side. So what we see there is a fluorinated carbon backbone. That's that zigzag line with all of the fluorines on it. And then off to the side of that, there's a whole bunch of other stuff. And what is actually in any given foam depends on the manufacturer, depends on when it was made, and it's often proprietary. So we don't necessarily know exactly what it is. But the point is that you have all this. You have the perfluorinated backbone, and then you have this other stuff. And that other stuff is actually subject to degradation in the environment. And so over time, you can lose that bit by bit, produce a series of intermediate transformation products, which are shown in the middle there. And then eventually you end up at perfluoroalkyl acids like PFOA, PFHPA, PFHXA, where all that's really left is that fluorinated carbon backbone and then a small head group like a carboxylic acid. So the legacy fluorotelmer foams were comprised of both short and long chain fluorotelmers. And the chain length there refers to the fluorinated backbone. Whereas the modern fluorotelmer foams, which are what is produced today, those are only short chain. So generally, those are not going to transform to PFOA in the environment because there just aren't enough fluorinated carbons in those molecules to make PFOA. But there may be some trace levels of PFOA or PFOA precursors left over from previous materials because those legacy fluorotelmer foams can transform to PFOA. So at our site, we believe that we have some of the legacy fluorotelmer foam, although mostly the modern fluorotelmer foam. But our concern was when we heat up the ground, if we do move forward with that process, if we heat up the ground, in order to remove the DNAPL and the chlorinated solvents, what could potentially happen to those PFAS compounds? If we have a lot of these precursor compounds, which is the fluorinated backbone plus stuff, are we going to enhance the rate of that stuff breaking down and then create the perfluoroalkyl acids? So we designed a bench scale study to try to mimic the conditions of in situ thermal remediation in soil and groundwater that we collected from the site, and then sent a lot of samples out for laboratory analysis by commercial labs to determine if the precursor transformation rate was higher, was faster in the heated reactors as opposed to the control or room temperature reactors. And the objectives of the study were to compare the rate of precursor transformation at the two temperatures, and then also attempt to quantify the mass of PFAS that we removed from the soil when it was being heated. So in order to answer these questions, we needed to use some special analytical methods. The standard PFAS methods, which probably most of you are familiar with, analyze for 18 to 40 specific PFAS compounds. The compounds that are found in foam and most of the intermediate transformation products are not on those analyte lists. So there was really no way for us to know how much PFAS was in the sample unless we attempted one of these non-target analysis techniques. So the first one that we did is called a total oxidizable precursor assay. And what this does essentially is that the lab takes your sample, and then they accelerate that transformation by using a fairly extreme oxidation process. And so they can take those precursor compounds and actually push them all the way to the perfluoroalkyl acids, which then they analyze using standard EPA methods. The other non-target method that we used was called extractable organic fluorine assay, or EOF. And this uses combustion to transform PFAS into fluoride, which is then measured. And so there's an analogous method here. The EOF is for soils. There's an analogous method for water samples. It's called AOF, or adsorbable organic fluorine. That is EPA method 1621. But there is no EPA method for EOF. As far as we can tell, it's lab-specific methods, SOPs. And same with TOP. There's no EPA method for TOP, at least as of right now. So here's our setup, and I want to give a lot of credit to my co-authors, Tiffany Duell and John Fitzgerald, who really put together this whole setup. A lot to look at, so we'll break it down a little bit. We put our soil into glass reactor jars, mason jars, 3 of which we put in the oven where we could control the temperature, and 3 of which were put on the lab bench. The ones that were on the bench were wrapped in foil to prevent exposure to light. And we know that the lab temperature is a bit warmer than we would expect to see in the subsurface, but it was the best we could do. So in order to accurately mimic our in situ thermal remediation scenario, we pushed air through these reactors, because in real life you would be pulling a vacuum on your treatment area, and so there would always be air coming in. We also thought that this was most conservative, as in most likely to encourage transformation to occur, because the literature suggests that these transformation reactors occur more or faster in aerobic conditions. So we wanted to make sure that there was a continuous supply of oxygen. Then, of course, we had to have our air coming out of the vessels. The heated vessels, as you might expect, there was a lot of water vapor that came out. And so we included condensers here, and we did accumulate a lot of condensate from those hot reactors. And then after going through the condensers, the air passed through 2 vapor capture cartridges in the lead lag configuration. Sampling air for PFAS can be really tricky. We went with a relatively simple setup where we used glass cartridges that contained PUF, or polyethylene foam, and XAD resin, with an attempt to capture as much of the PFAS as we could, although we don't really know how much passed through. And then, of course, we had, since we were evaporating quite a bit of water out of our heated reactors, we had PFAS-free water that we would add. So every time we would empty the condensate jar, we would add an equivalent amount of water plus about 10–20% in order to account for water vapor that was lost through the vapor stream. And here's a picture of our setup in the lab. John Fitzgerald really was the one who built all of this, and it looked very cool. It was quite loud, though, with those pumps running, because we ran this experiment for about 3 months. So for the summer months, the lab was not the most pleasant place to be. And you can see there's also a picture inside the oven. We had a thermocouple that automatically recorded the temperature every 5 minutes. So we were able to get really good resolution on our temperature, and then a NIST-certified thermometer to calibrate that. So here is our temperature profile that we established over the course of the experiment. Lasted for 3 months. We initially took about a month to bring the hot reactors up to temperature, which are there in red. So you can see the temperature on the y-axis and the time on the x-axis. We tried to raise the temperature at a relatively slow rate to somewhat mimic what would occur in situ thermal remediation. A thermal treatment scenario. We then held the temperature at 97 degrees C for 30 days. We picked 97 because we wanted to be just below the boiling point of water, mostly for logistical reasons, also because when the oven cycles on and off, there's some fluctuation in the temperature, and so we wanted that fluctuation to stay around 100 so that we wouldn't be actively boiling. And then in real life with thermal treatment, we would expect to see the temperature ramp down very slowly over time. Potentially a few degrees per month, but we need to get the data pretty quickly. So we elected to drop the temperature quickly and then hold it at 35 for the 3rd month of the experiment. We picked 35 C because we wanted to encourage biological activity. We thought that there may be some enhancement of biological activity at that temperature, which would again be conservative because we're looking at how we might maximize biotic reactions. So we took a number of samples throughout the course of the experiment. We analyzed most of those samples for PFAS by EPA method 1633. So we would basically take our jars, we'd open them, we'd give them a really good stir, and then take a sample and send that in for analysis by a lab. We also looked at the condensate. So at the end of each month, so after 30 days, after 60 days, and then after 90 days, we sent in composite condensate samples, which we analyzed for by EPA method 1633 for 40 targeted PFAS. And at those same times, we sent in the vapor capture cartridges for analysis by EOF. And so that's that total fluorine method that I mentioned earlier. I will mention that in the room temperature reactor, we never generated any condensate. So there were no condensate samples to send in, and the vapor capture cartridges were only sent in at the very end of the experiment, because we didn't expect to see a lot of PFAS vapor coming off of those. And then finally, we did the non-target analyses on the soil, both before and after the experiment. So trying to get a sense of the total PFAS, ideally for a fluorine mass balance. And then one more thing is that we added a bit of groundwater when we brought the reactors back down to 35C. We did that because we assumed that any microbes that were in the soil initially were likely killed off when it was held at 97C for a month. And so this was just to reintroduce those microbes. So preliminary characterization, we did collect groundwater and soil from the site. The groundwater had quite a bit of PFAS in it. The target PFAS was about 16 micrograms per liter. Normally we talk nanograms, so that's pretty high. We also looked at the top assay for that water sample, and we measured oxidizable precursors for an additional about 36 micrograms per liter. And then when we did the AOF analysis, which is now method 1621, we got another about 84 micrograms per liter of PFAS. So pretty high concentrations. We also collected soil from the site. This was superficial soil. It was collected from an area that was under a roof where the fire suppression system was present, and it was used for storage, barrel storage. So we sampled this, and then we sent off samples initially just to confirm it had PFAS in it, and it did have quite a bit. But unfortunately, our first finding is that these non-targeted methods are really not quite there yet for, especially for soil samples. And so here I'm showing our data that we received for extractable organic fluorine. This is that sort of total organic fluorine measurement that's used for soil. And we sent off soils to a commercial lab. They analyzed that soil in 2 different labs, so both under the same umbrella, but 2 different facilities. And they got values that were 20 times different. So we asked them, we had a call with them, and we asked them if they would consider kind of rerunning these analyses to see if there were differences in the SOPs that could potentially explain what they were seeing. They did rerun them for us and just essentially confirmed that the 2 labs are getting very different results. So we're talking about, this is the data here are in nanograms per gram of fluorine. So the difference is between about 500 and 7,000 nanograms per gram. So our hypothesis is that the soil is likely impacted by a complex mixture of complex PFAS, some of which are positively charged. And those positively charged PFAS likely stick to the soil pretty well. The extraction methods were developed and validated for anionic or negatively charged PFAS, which are generally going to be a lot easier to remove from soil. And there's some backing in the literature that this may be what's going on. So the methods that we've talked about, method 1633, that's the method for measuring PFAS in environmental samples, and it extracts those samples using basic methanol, so methanol that with a higher pH. And the EOF method that we received an SOP from the lab, the solvent they use is proprietary, but we believe that it's methanol or potentially basic methanol. And in both of those cases, it's unclear if anybody has really looked at how this could potentially extract the positively charged PFAS. So we did find the study here that looked at exactly this question: how do you get positively charged PFAS out of soil? And what they found worked the best was to use a 2-step extraction process, so basic methanol, but then also hydrochloric acid. And they found that some samples that were of soil that were impacted by AFFF contained up to 97% of the PFAS had a positive charge on it. So cation or zwitterion. And so we're wondering if perhaps a large chunk of those positively charged PFAS were not removed by the lab when they did their extraction. It's also possible that one lab is bringing in some inorganic fluoride. So lots of questions there. We're still working with the lab to try to better understand the data. Unfortunately, the top assay was also not quite as reliable as we had hoped. In this case, we sent the sample out for analysis by a different commercial lab, and the same subsamples were analyzed for PFAS using both 1633 and then also the top assay, which uses a modified method 537.1. And the real takeaway here, especially if you look at the bars there on the right where it says post-experiment heated, that if you look at the same set of 33 individual PFAS and you sum them, we actually got a higher concentration using method 1633 than we did post-oxidation in the top assay, which really doesn't make any sense because the top assay should capture all those target analytes plus the precursors. And so the fact that it was measuring less, target analytes than we got in 1633 is a bit concerning. So limitations here, which we knew there were some limitations with top when it comes to soils, that not all the precursors transform. So that's important to know. You're measuring oxidizable precursors, not all precursors. And then you can also have some chain cutting, which means that the precursors, that fluorinated backbone can actually be cut. So even if your precursor has, say, 6 carbons, after it has a 6-carbon perfluorinated chain, after oxidation, it might drop to 5 or 4. And so anything then that drops below 4, you wouldn't see in your analysis because the analytical list only goes down to a 4 perfluorinated 4 carbons. So, but we did still learn about our soil. We learned that it was dominated by PFOS, which was a little bit of a surprise because we don't think that first generation foam, which is rich in PFOS, was ever used at this site. And then also PFOA. We suspect that the PFOS and maybe also a good chunk of the PFOA is actually coming from a non-AFFF source. After the sample was oxidized in the top assay, we saw an increase in both short and long chain PFCAs. And so that's likely the foam that is then producing, after oxidation, it produces those PFCAs there. So that's where the dark blue lines are a lot taller than the light blue lines. That's new stuff that came from the precursors. So in the groundwater, we saw quite a different signature, and note the logarithmic scale on the left. There's almost no PFOS in the groundwater. We're talking about maybe 15 nanograms per liter. And then if you look at those FTS compounds, which are intermediate breakdown products of the foam, it's well over 1,000, close to 10,000 nanograms per liter. So the groundwater was very clearly impacted by the fluorotelomere foam and not by that first generation of foam. And after oxidation, not surprisingly, we saw an increase, significant increases in the short chain, mostly short chain PFCAs. So we're talking the C4, which is PFBA, B stands for butane, up to PFHPA, where the HP stands for heptane. So that's the 4 to 7 carbon perfluorinated chains. All right, so before we actually got started on our experiment, we wanted to ensure that the concentrations were consistent across the 6 reactors. We ran everything in triplicate so that we would have some statistical power. And generally, we did see that to be the case. So just a quick reminder of what we did. We heated up our soil, we kept it hot, and then we dropped the temperature. And our first finding here is that we did see an increase in PFCAs in the hot reactors relative to the control reactors. So this indicates to us that some precursor transformation occurred and that more precursor transformation occurred in those hot reactors than it did in the room temperature reactors. Here, I'm showing you data for PFHXA. The red lines are the heated reactors, the blue lines are the room temperature reactors. And you see there's 3 red corresponding to the 3 reactors in the oven versus the 3 on the bench. So specifically, what did we see? Well, while we were ramping up the temperature, we saw a 300% increase in PFHXA. And then when we were at elevated temperature, initially we saw kind of a flat profile, and then we actually saw a drop in PFHXA concentrations, which is interesting because these are forever chemicals. We're not supposed to break them down. So there's a question of where did they go? And then at the end here, we saw another increase. So important to note that we expect there was biological activity during the first month and the third month, but not during the second month because the microbes would have all been killed by the heat. And this increase that we saw was not just PFHXA. We saw it for other compounds too, and it was statistically significant. So showing the same kind of graph here for 6,2-FTS, where we saw the concentration increase, then remain steady and even drop, and then increase again a little bit in month 3. And then here's PFPEA. So that's the 5-carbon perfluorinated carboxylic acid. And just here we kind of grouped them a little bit by type. So if we look at those, the C4 through C6 PFCAs in the heated reactors versus the control reactors, and then also those FTS compounds, which are intermediates in the heated versus the control, you can see that there was clearly an increase that was statistically significant in those heated reactors. So that says to us that transformation absolutely did occur faster in those hot reactors than in the room temperature reactors. Now, we did not see a difference between the heated and control reactors for PFOS. This is not surprising because PFOS is not a transformation product of the fluorotelomere foams. So this result was somewhat expected. What was not expected is the amount of variability that we see in those values. We worked really hard to homogenize the soil, and certainly looking at other PFAS, we saw pretty consistent results across the groups of reactors. So the fact we see so much variability here is a little bit unexpected. And now we can look at PFAS-6. We care about the sum of the Massachusetts PFAS-6 because that's where we have our drinking water standard, or MCL. And what we saw is that if you take an average, sure, we had higher concentrations of PFAS-6 at the end of the experiment in the heated reactors versus the control, but that difference is not statistically significant, essentially because of the variability, especially within the control reactors. We can't claim that those are actually different. So here's just a bar graph showing those final concentrations for the 3 heated and the 3 control. The 3 heated reactors are pretty similar, but there's a lot of variability in the control. And this we think is because that the PFAS-6 was dominated by PFOS, and also where there was no change, which was expected, and PFOA. So what's going on with PFOA? So initially PFOA looked a lot like the other PFCAs. We saw the concentration in the heated reactors start to increase as we increased the temperature. But by the end of the experiment, there was so much variability that we really couldn't say one way or the other whether PFOA actually increased in the heated reactors. Again, that variability was mostly in the control reactors, and we don't have a good explanation for why that occurred. We suspect that there may be a non-AFFF source of PFOA, but that still really doesn't explain the kind of crazy variation that we see there. So if anyone has any thoughts on this, we'd really appreciate your input. So our third finding is about evaporative loss of PFAS. And this was a little bit of a silver lining because we're out there, our goal is to address the chlorinated solvents, but we also know we have PFAS. And so if we can remove some of that PFAS during our thermal remediation, that would be wonderful. And so here, as I mentioned, we had condensate, which we analyzed for PFAS. We also had those vapor cartridges, which we analyzed for PFAS. And what we found was that quite a bit of fluorine, so here we're measuring micrograms of fluorine, quite a bit was removed. We expect both of these to be underestimates, in part because we are only looking at the target analytes in the condensate, and because we didn't really necessarily expect to capture all of the PFAS that was in the vapor moving through those cartridges. So we did see some PFAS removed, mostly in the vapor cartridge, and this definitely has implications for waste management of the media that's used to clean up the vapor and the condensate when it comes time to build out our full-sized remedial technology. What kind of PFAS did we detect in the condensate? This was also interesting to us. As we were warming up the reactors, we saw mostly, so that the top graph there, we're looking at concentration on the y-axis and then individual PFAS along the x-axis. And what we saw in the condensate initially was PFOSA. This is a pretty volatile compound that's actually a PFOS precursor. And then when we were at our elevated temperature, we saw high concentrations. So that's up to about 900 nanograms per liter. We saw the PFOSA again, but we also saw some PFCAs. So PFOA was in there, PFHXA. And including some pretty heavy ones where we wouldn't necessarily expect them to volatilize, even at 97C. And then in the last month, we saw much lower concentrations, much less condensate generated. And again, mostly a shift towards the volatile compounds there on the right. But we also saw some, this is very unexpected, PFDOA. So that's the 12-carbon carboxylic acid. We really would not expect to ever vaporize that. So our thought is that those large PFCAs that we see in the condensate are unlikely to be from direct volatilization. We don't think they're from particulates either because our airflow rate was not very high, but they may be transformation products of volatile precursors. We didn't measure those volatile precursors, but we did potentially measure the transformation products. And especially at that last month, since we were producing much less condensate, we didn't empty the jar into our sort of storage in the fridge as often. And so there was potentially more time available for transformation to occur at moderate temperatures. And then our last finding, which is kind of gets back to the heart of the issue, is we did see this precursor transformation occur. We measured it, but was it significant? And what we concluded was that it was probably pretty small. So we did have more measurable PFAS in our reactor at the end of the experiment, the end of the heated experiment. If you look at the target analytes in 1633, we increased by about 150 nanograms per gram. If you look at EOF, we increased by about 500 nanograms per gram. So that's telling us that, yeah, some of that PFAS became more extractable, and it was pushed towards those target or terminal transformation products. And if we looked at the control reactors, similar story where we actually did see transformation occur. We were able to measure it, both in terms of the target analytes and the extractable fluorine. But the starting fluorine concentration we expect was at least 7,000 nanograms per gram. And so this increase of 150 is actually pretty small in the scheme of things. We estimate that approximately 2% of the total fluorine mass in the soil in those heated reactors was transformed from an immobile precursor to a more mobile PFAA. And in the control reactors, that would have been significantly less than 1%. So what that tells us is that, well, if we do this in situ thermal remediation, there will be some transformation, but it's going to be pretty small. There's going to be still a large reservoir of PFAS remaining in soil at the site. So a quick summary, I think I'm over my time, but essentially what we found is that these non-target analysis methods have limitations. We did see the precursors transform faster at higher temperatures, but we don't think that transformation is going to be especially relevant in terms of both the mass produced and also the specific PFAS that are produced. They're mostly not PFAS that are in the PFAS-6 because they're the very short chain PFCAs. In fact, we didn't see any significant difference between the heated and control reactors for PFAS-6. We confirmed that we should expect to see some evaporative removal of PFAS. So the findings of the study suggest that there will be little to no impact on down gradient receptors based if the thermal treatment is selected as the remedial alternative at the site. But certainly time will tell. And so there will be robust monitoring to ensure that nothing unexpected happens. And so that's what I have, but I would definitely appreciate feedback if there's time.
Thank you, Natalie. Much appreciated, especially going through robust test driving using benchmark studies to have a glimpse for what we are, any potential unintended consequences in the selection of a remedy. And for sure, we'd like to at least respectfully request for the advisory committee members or LSPs or the community at large tuning in this morning, if you have any comments or wish to continue our dialogue on this particular experiment designed by the Northeast region, we would really like to ensure that we have that dialogue. And we appreciate the advice from the advisory committee, certainly. Well, thank you, Natalie. Much appreciated. Thank you for your time and hard work.